Hey everybody, so this week we're going to focus a little more on inequalities. We're going to start by talking about a couple interesting cases that happen with compound inequalities, and then I'll transition into absolute value inequalities. So to refresh our memories, remember with compound inequalities, we either have and compound inequalities or compound inequalities. Remember the graph of an or compound inequality looks like this, where it's either pointing over here or it's pointing over here and it's not in the middle. Remember then, and compound inequalities is like this, where one is on top of the other and we no longer have those arrows. So I'm going to start by looking at one of the more interesting cases with an OR problem. So in this one here, I've got -9 is greater than or equal to -2x minus 3, or -2x minus 3 is less than or equal to -19. So as you can see, I've got that -2x minus 3 that is common in both of them. And we got to figure out which cases of x satisfy one or the other. All right, so here I've got -9 is greater than -2x minus 3. Since it's an OR problem, I can just do them separately and combine them at the end. So this one here, I'm going to make my t-chart. I'm going to add 3 to both sides. That's going to leave me with -6 is greater than or equal to -2x, because these cancel out. Then I'm going to divide by -2. Remember, since I'm dividing both sides by -2, that inequality's got to flip. So I get +3 is now less than or equal to x. Now, remember, my tip on these is always to flip everything if x is on the right side. So x is greater than or equal to 3. Now I'll do a similar thing to the problem on the right. Make my t-chart, add 3 to both sides. That leaves me with -2x is less than or equal to -10. Then I have to divide by -2, and just like we did over here, we got to flip that inequality. So it becomes x is greater than or equal to +5. And I don't need to flip anything because x is on the left side. Now, one interesting thing that you might see here is both of these say greater than or equal to. That's what makes this an interesting case. So right now I've got x is greater than or equal to 3, or x is greater than or equal to 5. Now, in order for this inequality to be totally true, it either has to be greater than or equal to -3, or it has to be greater than or equal to 5. So let's look at what this looks like on a graph. If I graph it, and I have 0 here, 1, 2, 3, 4, 5, then if I look at it on a graph, if I graph that first part, I've got a closed circle on 3, and it's shaded to the right because it's greater than. And then this one is a closed circle on 5, and it's also shaded to the right. Now, in order for this to be true, it has to be in either one of these. However, if we look at this here, what do we notice about the graph? Well, this first graph here, x is greater than or equal to 3, is going to satisfy everything. Because if it's in this one, it's going to be in this one too. Or if it's in this one, it's going to be in this one too. So the answer to this one is just x is greater than or equal to 3. So when they're both going the same direction and we have an OR problem, that means that it's going to be whatever the one is that's the biggest, or whichever one consumes the other one. See how this graph consumes this graph? That means that this graph is going to be our final answer. So that's interesting case number 1 when we deal with OR problems. Alrighty, next interesting case is another OR problem. Here we've got -x plus 6 is less than 12, or -x plus 6 is greater than 2. So same process. I'm going to go through, make my t-chart. This one's pretty easy. I just have to subtract 6, so I get -x is less than 6. Then I got to get rid of that negative, so I'm going to divide by a -1. Since I divided by a negative, I have to flip it, so I get x is greater than -6. Scoot over to the other one, make my t-chart, same process, subtract 6, get -x is greater than -4, divide by -1, flip the inequality to get x is less than 4. So remember, this is an or problem. We've got x is greater than -6 or x is less than 4. Think about what this looks like on a graph. If I've got -6 over here, +4 over here, which means that 0 is somewhere in there. If I graph the left one, I've got an open circle on -6, and it's shaded to the right since it's positive. Or x is less than 4, which is an open circle on 4, shaded to the left. So you might be thinking to yourself, this looks like an and problem. And you're right, this does look like an and problem. However, it's an or problem. If we get a problem that's an or problem, but the graph overlaps like this, and it looks like an and graph, that means that we have all real solutions. Because in order for this inequality to be true, it either has to be in this graph going this way, or it has to be in this graph going this way. And those lines, those have arrows on the end. They're just going to keep going. So if they're just going to keep going like that, and it has to be somewhere on that line, it has to be somewhere on the number line, which is all real solutions. Now, when you're doing this on Delta Math, you'll probably not see a solution written like this. What you'll probably see instead is where they give you a double bar R. And that double bar R just means all real numbers. So to reiterate, if you get an or problem and the graph ends up looking like an and problem, you're going to get all real solutions. Really briefly here, I'm just going to go over what the and version of that interesting case looks like. So let's say you're going through a problem, you're going through a compound inequality problem, and it starts out as an and, but then you get down to it, and this is what your solution looks like. Now, normally you'd want to try to combine it into one thing. However, x is less than 10. It's not greater than 10, it's less than 10, but it's greater than 12. So if you think about what that looks like on a number line, if I've got 10 here and 12 here, that means that this one over here says it's an open circle shaded to the left, and this one is an open circle shaded to the right. Now, you might be thinking, this is where Mr. G did his little dance, so this is an or problem. However, this started out as an and problem. If it starts out as an and problem and it's pointing in two different directions, then we have to think about it, because it's saying that in order for this inequality to be true, x has to be somewhere in here and in here at the same time. Normally it's shaded in the middle, so it works out because it satisfies both, but it's impossible for a number to be both here and over here. You can't pick a single number that's in both of those graphs. So for this one, there's no solution. So if you get an and problem that ends up looking like an or problem, you get no solution. And again, Delta Math makes it look a little bit different. Instead of saying no solution, it'll probably give you this symbol here, which is the symbol for an empty set, meaning there's nothing in the set of real numbers that could satisfy that quantity. All right, so now we're going to transition into absolute value inequalities. And this is where I am super, super obnoxious with you guys, because it's super, super important to remember whether we're doing a greater than problem or a less than problem, because that'll tell us whether it's an and compound inequality or an or compound inequality. So I want you to write this down exactly like I have it written and think about, so with compound inequalities, you could have thought about my little dance moves that I did. In this one, I want you to think about me being super, super obnoxious. If you have an absolute value inequality, and this is like the absolute value of something is greater than a number, then it becomes an or problem. And I want you to remember it by saying absolute value of x plus something is greater than a number. So that becomes an or compound inequality. On the other hand, is if we have a less than absolute value inequality, like if we have the absolute value of x minus something is less than a number, then I want you to think about it as an and problem. So think about it, me being super obnoxious, the absolute value of x minus a number is less than another number, then it becomes an and problem. So write this down and we'll see what that means here when we do a couple examples. All right, here we go. First example problem, we got the absolute value of x minus 2 is greater than or equal to 12. So did you catch the drift there? That's greater than or equal to 12. So think about what that means. If I said greater, it's going to end up being an or compound inequality. So here's what we're going to do. We're going to break it down into two inequalities. So I'm going to break it down over here, and I have x minus 2 is greater than or equal to 12. So just the original inequality in there. Then what I'm going to do is I'm going to break it down. I'm going to say or, that's why I did the greater than, x minus 2, and I'm going to flip both of these, meaning I'm going to make this less than or equal to, and I'm going to make this a negative. Less than or equal to negative 12. Then it's just like what we did before. So we broke it down into two things. Now it's just a compound inequality that we need to solve. So I'm going to t-chart over here, add 2, and x is greater than or equal to 14. Over here, I'm going to go through that same process. T-chart, add 2, x is less than or equal to negative 10. Then let's look at what that looks like on a graph. If I graph it, I've got negative 10 over here, I've got 0 somewhere over here, and then I've got 14 down here. This part over here, x is greater than or equal to 14, means a closed circle on 14, shaded to the right. This is a closed circle on negative 10, shaded to the left. So when it's the original problem, or when you get the absolute value isolated, that's going to be key. We're going to look at that in the next example. When we get that absolute value isolated, then we look at what that symbol is in the middle. If it's greater than, it's an or one. If this was less than or equal to, then we think less than, and it would be an and problem. All right, so in this next one here, it looks super scary, but we're going to do this in a few steps, and it's not going to be too bad. So we've got 5 times the absolute value of x plus 5 plus 3 is less than 28. So you might be thinking to yourself, we've got less than, so this is probably going to be an and problem. But we can't decide that until we get the absolute value by itself. So you're going to treat this as if you were trying to solve for this, trying to get this by itself. So treat this like you would if it was just like the letter A. If it was 5a plus 3 is less than 28. So the first thing I would do would be to subtract 3 from both sides to get it to be 5 times the absolute value of x plus 5 is less than 25. Still, I want to try to get that absolute value by itself, so I'm going to divide everything by 5. So I'm going to get absolute value of x plus 5 is less than 5. So now this one looks very similar to the previous problem because we've got the absolute value of something and then an inequality and then a number. Now, our prediction was correct. We still have that less than, so it's going to be an and problem. If this was a negative 5 and we divided both sides by negative 5, that inequality would still flip and it would switch it to an or problem. But since it was all positive, we divided by a positive, it stays an and problem. So just like we did before, we're going to break it up into two different problems. We've got x plus 5 is less than 5. Just the original thing without the absolute value. But then we also say and x plus 5 and flip both of these is greater than negative 5. So now I'm just going to go through and solve each of them. Make my t-chart, subtract 5, x is less than 0. Over here, do the same thing, subtract 5, x is greater than negative 10. So then if we wanted to combine it into one inequality, we know that it's greater than negative 10, so this is an and problem, so we've got negative 10 is less than x, which is less than 0. So then on a graph, we've got negative 10 over here, got 0 over here. It would be an open circle on both and shaded in the middle. So when you're solving absolute value inequalities, you got to get the absolute value part by itself. So you treat it like you would if it was just a letter or a variable. Get it by itself, then decide. If it's less than, it's an and problem. If it's greater, then it's an or problem. And then it's just doing it like we would a normal compound inequality.